Okay, so this is essentially asking us how many different ways are there to pair within one group. So the previous time we were mapping between our order and our set. This time we're pairing up within our set. So I'm going to actually start off with a slightly easier question, and we're going to look at how many different ways there are to pair up to. This is just one. There's just one way to pair up the two people, right? Because one is with two. I don't actually care about the ordering within this. How about four? So four, we have, for four, we can have one paired with two and three paired with four. We can have one paired with three and two paired with four. Or we can have one paired with two and then one paired with four and then two paired with three, right? So this right here is going to capture all of the possibilities for four. What about six? 6 players. So we can have one paired with two, and then three paired with four, and then 5 paired with six. We can have one paired with three, and then two paired with, let's do different order. Let's do one paired with two, three paired with five, and then four paired with six. We can do one paired with two, and then three paired with six, and then four paired with five. Now we can move on to one paired with three, and then two paired with four. And then we're left with five paired with six, one paired with three, two paired with five, and then four paired with six. One paired with three, two paired with six, then four paired with, four paired with five. Cool. And now we can move on to all the things with one paired with four, all the elements with one paired with five, and all the elements with one paired with six. But if we notice something, both of these guys look like one paired with two. And then something that's essentially the same as all of these pairings, right? Because we have four remaining elements that we still need to pair up. And that's just the same thing as asking how many different ways are there to pair up four elements. So for one paired with two, we got the three elements that we got up here, or something that looks kind of like those three elements. And we got the same thing for one paired with three. Now, for one paired with four, we're also going to get the three different branches. And one paired with five, we're also going to get those three different branches. Same thing with one paired with six. So here we get 5 times 3, which also happens to be the same thing as times 1. Now, what happens if we do all of the options for 8? So then I have 1 paired with 2. But then once I have 1 paired with 2, I have 6 remaining objects left that I can permute, that I can pair up, which is going to look basically the same as all of these guys. I can just reassign the numbers, and I'd get sets that look like all of these guys. So, and that's 15 options. Do the same thing with 1 paired with 3 times those 15 options. 1 paired with 4, 1 paired with 5, paired with 6, 1 paired with 7, and 1 paired with 8 times each of these guys then has 15 options afterwards. So how many different options are we going to have? 1, 2, 3, 3, 4, 5, 6, 7. And that's because I have 8 things in my list, and then I have 1 paired with each of them. So that means that I only have, because I can't double up on 1, that means I only have 7 objects left. So that means I have 7 times 5 times 3 times 1. This is sometimes written as 7 double factorial, meaning that we skip every other number. So the natural thing here is the general formula is going to be n minus 1 double factorial. N minus 1 because here we have that 7. Here we have 6. This guy we can write as 3 double factorial, even though it's just 3 times 1. So it's a little bit odd to write it that way. And then this guy is 2 minus 1 double factorial, or 1 double factorial. So the general formula is going to be n minus 1 double factorial, meaning that we skip every other number. So